Are y'all going to do Christmas at CSU tonight? I don't know. I don't know what it is. Somebody asked me if I was going. I don't know. It's 80 degrees outside. That feels wrong. What? Maybe I should bring my... Is that why the cap's closed? Which is always apparently when Christmas at CSU happens. They always line up. Has it always been this early? That feels different. It has always been this early? Oh, okay then. All right, so we are doing, we're continuing induction. Tying your cords in knots is the right choice, right? Right, knots are good. Okay, so we are going to continue doing induction, and then we're going to do strong induction, hopefully today as well, and then we'll do some recursive stuff on Monday, test on Friday. So we are doing induction now. We're going to prove that n squared is less than 2 to the n if n is, on homework 10, I don't have that with me, but on one of them I don't give you a, on number 5, that should be for n bigger than or equal to 0. Number 5, I didn't give you restrictions on n, it should be n bigger than or equal to 0 on homework 10, number 5. Homework 10, number 5, n greater than or equal to 0. Homework 10, Emily. Homework 10, number 5, n is greater than or equal to 0. Okay. Induction. We want to prove that n squared is less than 2 to the n if n is bigger than 4. So we got to do a base case, get on the ladder. What is our base case? N is equal to 5. So we need to know, we need to look at 5 squared is 25, and 2 to the 5th is 32. And I would say something like, clearly, 25 is less than 32, so we're good to go. Now, I wouldn't write 25 less than 32 to like start with, or like, I wouldn't write 5 squared less than 2 to the 5th to start with, because, you know, that's the thing you're trying to prove. Okay. So the base case holds for the inductive hypothesis. We want to assume for some integer k with k bigger than or equal to 5 that what? That k squared is less than 2 to the k. And then what do we want to look at? Or what do we want to show? And this part is where we're going to do a proof. Okay. Can we go ahead and write? Proof. We will prove by induction that n squared is less than 2 to the n for all integers n greater than or equal to 5. Or you can write greater than 4, I don't care. All right. For the base case, consider n equal to 5. Notice 5 squared is 25, and 2 to the 5th is 32. Clearly, 25 is less than 32, so the base case holds. For the inductive hypothesis, assume for some integer k greater than or equal to 5 that k squared is less than 2 to the k. Good? Any questions so far? Okay, I'm going to consider k plus 1 squared, which is equal to k squared plus 2k plus 1. Which is less than 2 to the k plus 2k plus 1 using the inductive hypothesis. Yes? Okay. I have to figure out a way to make this look like 2 to the k times 2 or so, or 2 to the k plus 2 to the k, which would be 2 to the k times 2, which would be 2 to the k plus 1. Yeah. I've got some addition stuff happening. I've got to fill in. This is the part where mathematical creativity comes into play. I have got to make this look like 2 to the k plus 1, which is 2 times 2 to the k, which is 2 copies of 2 to the k. Yeah. So I'm gonna play with this. This is less than 2 to the k plus 2 to the k plus k, because k is bigger than or equal to 5, right? So certainly bigger than 1. And then that's 2 to the k plus 3 times k. This is less than 2 to the k plus 2 to the plus k squared. I'm so sorry. Plus k squared. This is all because, well, this is just combining like terms. This is because k is greater than 5. So 3 times k has to be less than 5 times k, which is k squared. Yeah, or k times k. All right. But then I'm going to use the inductive hypothesis again. Is this the only way to do this? No. Did I look at anything before I started doing this right now? No. Was it the best way? I have no idea. But this, by the inductive hypothesis, again, is less than 2 to the k plus 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. What do you think? What? What? Oh, because this exponent, you have like bases, you just add the exponents. Thoughts? Oh, don't overwhelm me with all of your thoughts. Thus, k plus 1 squared is less than 2 to the k plus 1. So we have shown n squared is less than 2 to the n for all integers n greater than or equal to 5. Let's see how I did this before. I'll do it the exact same way. Just gotta have mathematically true things that keep the inequality going the same way. That string of inequalities / equalities is okay because they're all going the same way. So I can say that the beginning thing is actually smaller than the ending thing. Okay. Do you have any other questions about any questions at all about number 5? No, we don't. Okie dokie, let's do number 6. Alrighty. What would our base case be? Oh. N equals 0. I'm not going to write that 4 divides thing because I don't know that it does. 9 to the 0 minus 5 is equal to 1 minus 5, which is negative 4. And then I would say that clearly 4 divides negative 4, so the base case holds. Good? For the inductive hypothesis, we're going to assume for some k greater than or equal to 0 that 4 divides 9 to the k minus 5. What does that actually mean?
9 to the k minus 5 can be written as 4 times some integer.
Yeah. And what are we trying to show? That 4 divides 9 to the k plus 1 minus 5. And what does that mean? Yeah, but with a k plus 1, right? 9 to the k plus 1 minus 5 is 4 times an integer. Yes? Okay. I'm going to start writing a proof and then see when I need my scratch work back, okay? Are you guys okay with that?
Yeah.
Alrighty. We will prove by induction that 4 divides 9 to the 5th minus, no, 9 to the n, I'm so sorry. That was going to get a whole lot easier. 9 to the n minus 5 for all integers n greater than or equal to 0. For the base case. Let n equal 0. Notice 9 to the 0 minus 5 is negative 4. Clearly, oh, it doesn't look very clear. Clearly, 4 divides negative 4. Thus, the base case holds. Ooh, I got very sleepy just now. Wake up. Of course. Yeah. Do you want to see a picture of them? They're adorable. Pirate and oh crap, what's that person's name? Mirabelle from Encanto. What? I don't know why my son is not smiling. I bet I could find a picture of him actually smiling. Oh well. They had a good time. It was a late night and therefore an early morning, so we'll see how they did at school today. Do what?
Eating all that candy.
Oh yes. They're going to have so much candy. I'll show you what my daughter looked like today going to school too. Today was Wacky Friday. Like really though. She's wearing Mater socks and boots. St. Patrick's Day skirt. Glow sticks from last night and her candy corn Halloween shirt. She does. But it's like really her life. She's just living her best life. She's pretty wacky every day. So today she has justification, I guess. So
She's been preparing all her life.
she has. She has. She's been waiting for her moment. So it's fine. She went as Elsa to school yesterday, but then Mirabelle last night for trick or treating, and she went as Cinderella to church on Sunday. Like I don't know what's happening. It's just like whatever. Just do whatever you want, and the rest of us are just here. It's okay. So they had a lot of fun, but we left our friend's house at 9:00 last night, and so it made for a late evening with them because they're normally in bed at 7:30, and so my daughter cried the whole way home because I wouldn't let her. One of my best friends decided to make cupcakes for dinner last night. We're going trick or treating. Why are you giving them cupcakes? I don't understand. But she insisted on giving them to my children. And she didn't give them like mini cupcakes. She gave them full cupcakes. I was like, okay. And then when we were trying to leave, she got Ziploc baggies. They just went trick or treating, right? She got Ziploc baggies and filled them up with Nerd clusters and Skittles. And gave them to my children. And the kids, she always gives my kids snacks to eat on the way home. Always. That was like popcorn or, whatever. But last night it was like more candy, and I was like looking at her and she was doing this to me. And I was like, I'm going to, but we didn't let Ellie have any on the way, either of the kids have any on the way home. And my daughter cried for the entire 20-minute drive to our house, and then cried while she was getting in bed. Finally goes to sleep, and this morning she comes out of her room, and the first thing she says to me is, Mom, did you remember about my Nerds and my Skittles? I wish that you hadn't. Yeah, I did. But yeah, so, but, we're not going to like take their candy from them or anything, but we're going to definitely make it last till Christmas time. I mentioned like red dye. Maybe that Riley, my son, shouldn't have any because I think he has ADHD, and like, your diet matters, and I don't think you should have red dye. And so every time you like eat something, my daughter's like, "Hey, that's got red dye." It's okay. It's okay. It's not that much. Okay. No Twizzlers. Well, it tastes like garbage anyway, so Like, why are you chewing on hard plastic? I don't understand. The ones that are like softer, those are good. That are like strawberry flavored.
Yeah, like those are better.
But like, now a regular Twizzler, it's trash candy. That's trash. Okay. Clearly, 4 divides -4, so the base case holds. Thank you for letting me have a moment to wake up. I feel better now. Hope you do too. So we are going to assume the inductive hypothesis. So for the inductive hypothesis, I put a dot on an I there that doesn't exist, so that's fun. Good luck figuring that out. For the and not dotting the I's that are there. It's all good. For the inductive hypothesis, assume for some integer k greater than or equal to 0 that 4 divides 9 to the k minus 5. I'm going to say that is, oh, not all is one word. That is 9 to the k minus 5 equals 4a for some a in z. You have a problem really similar to this on your homework for Monday. But these two that we're doing now will help you prepare for those. Alrighty. So we're going to say consider 9 to the k plus 1 minus 5. Right, this is the thing I need to show. I got to do the proof in here. That's what I'm doing now, or trying to do now. I have some options. I'm going to kind of play around with things, but I would like to have either, I would like to be able to use this. So I can solve that for 5, I guess. I'm not going to do that. I could rewrite this. Y'all let me just think for a minute. If I rewrote this as 9 to the k times 9 minus 5, that doesn't go in there, times 9 minus 5. Are we okay with that? And then this thing, if I use that, that would be that 9 to the k is equal to 4a plus 5. Yeah. I should have done this in my scratch work instead of in the middle of my proof. It's fine. I can go back and do that right now. 9 to the k is 4a plus 5. So I'm going to use that maybe right here. 4a plus 5 times 9 minus 5. Is this going to work? 36a plus 45 minus 5. Oh, yep, sure does. 36a plus 40, which is 4 times 9a plus 10. That's 10. I'm good. I'm supposed to be taking a 4, not a 9, and I wasn't even doing that right. Okay. Brian, why are you looking at it like that? Did I do it wrong?
It looks like it says 4 at 5 on the line in the parentheses. Oh, a plus 5.
4a plus 5.
Oh, what?
Huh?
I don't remember that from math.
No, that's a plus 4a plus 5 from this. TA, yes, whatever. We're doing our best. 4a plus 5 times 9, because I replaced 9 to the k with this. Okay, and then distributed that 9, and then subtract 5, so we got this. Okay. So we'd say something like, since 9a plus 10 is in z, 4 divides 9 to the k plus 1 minus 5. We have shown 4 divides 9 to the n minus 5 for all integers n greater than or equal to 0. All right. How do we feel about number 6? Good? Any questions? No? Michael?
Never mind, I see.
Okay. This is 9 to the k plus 1 because 9 and 1. K and 1. Okay. All right. Let's do this one. Yeah, wait. Do y'all want to try to do this without me and see what happens?
Yeah.
Yes. Do it. Hmm. Mm-hmm. 5 times 3. Yeah, that's okay. Weird. Sure does. Mm-hmm. Yes. Yeah. 5 does divide 0. Okay. 0 times.
0 times anything, or 0 times 5.
5 divides 0. The 0 is 5 times 0. Yes. There is an integer, yeah. Oh no. You gotta do k plus 1 to the 5th?
Yeah.
I'll just tell y'all what that is in a moment. How about that? I don't remember the triangle rule. Brian, do you remember the triangle rule for expanding a binomial? Yeah. This is to the fifth, to the fourth, to the third squared and 1, and then it's like 1, 5, 10, 5, 1. I don't know. I'll tell you in a minute. Let's see what it is. Let's.
I was trying to figure out if there was a better way to do this than just FOIL out.
Yeah, there's Pascal's triangle thing is how you would do it, shortcut. But I'll just tell you what it is. How about that? I did it with the internet. I was like, K plus 1 to the fifth. Okay. I'm gonna write a proof if y'all are ready for me to. Okay, sounds like y'all are all at that stage, right? We will prove by induction that 5 divides into the fifth minus n for all integers n greater than or equal to 1. For the base case, let n equal 1. Notice 1 to the fifth minus 1 is 0, and 5 divides 0. So the base case holds. Now, for the inductive hypothesis, assume for some integer k greater than or equal to 1 that 5 divides k to the fifth minus k. That is k to the fifth minus k is equal to 5a for some a and z. Are we okay with all of that? Okay, what is the thing that we're trying to show? Is equal to 5 times an integer, right? Or that 5 divides that thing. All right, so the proof is this part. We're going to start with the left-hand side there. Consider k plus 1 to the fifth minus k plus 1. All right, ready? K to the fifth plus 5k to the fourth plus 10k cubed plus 10k squared plus 5k plus 1. That's k plus 1 to the fifth. Hey, yeah, I did that, didn't I? 1, 5, 10. I didn't have enough terms. I didn't have my constant term. I only have 1, 10. 1, 5, 10, 10, 5, 1. So close. But then I got to subtract off the minus k minus 1. So minus k minus 1. Or minus k plus 1. All right, y'all. I'm going to rewrite this in a way that puts k to the fifth minus k together. Yes. Instead of combining that with a 4k, because that wouldn't super be helpful. Maybe it would be because you can move things around, but I'm just going to do that. Are you okay with that? And also, plus 1 minus 1 cancels each other out. Look at everything else that's left behind. What's true about all those green things? They're divisible by 5, and that's what we're going for. What? Yeah, they do. You could. I thought you said, would you pull the K out of 2? And I was like, where is there a 2 besides that squared? I was confused. Like, oh, no. Okay, so this is K to the 5th minus K plus 5K to the 4th plus 10K cubed plus 10K squared plus 5K, which is equal to 5A plus 5K to the 4th. Is it helpful if I shout at you? It feels like probably not. Our air conditioner went out in our house, you guys. Yeah. It's been like 80 the last couple of nights. I'm like, come on. Can we just get like a fall day? Because, you know, it feels so stupid to pay to have your air conditioner fixed right now in November.
Ride it out.
Right. Can we ride it out? I don't know, because I thought I was going to die last night. So I hate air blowing on me, too. Hate it. So, like, a fan, you know, we've got 3 fans and the windows open or whatever, but I cannot stand air blowing on me, so I have to have covers on me. But then I'm hot. So we were supposed to have people over, and I was like, tonight, I was like, I don't think we should do this. It's 80 degrees in our house. And right. we can't have any more candy in the home. Yep. Thank you. I just pulled whatever out I wanted to, apparently. 2K cubed plus 2K squared plus 1. Okay, that looks better. And then I'm going to say since A plus K to the 4th plus 2K cubed. My writing doesn't look like it makes sense anymore. 2K squared plus 1 is an integer. 5 divides K plus 1 to the 5th minus K plus 1. We have shown. Do y'all realize how much work this is? How like powerful this tool is? What a strange thing you just proved. And that proves it. It's weird. Induction's great. We have shown that 5 divides into the 5th minus n for all. Brian, you do the, sorry, my brain is all over the place. You do the chemistry group tutoring stuff?
Yeah.
How much do you get paid to do that?
I think it's the same amount as normal.
As like normal hours?
Well, yeah, I'm putting it, it's part of the normal hours.
For like the TA job? Or like you bill it the same way you bill any tutoring?
It's done the same way as any tutor.
They should pay you more for that. I'll get that worked on. I'll get that worked on for you, Brian.
Thank you.
But it's well attended?
Well, people could make multiple, sometimes.
Do you lead it for a group in a room?
For organic chemistry, yeah.
Not in the library through the Buck Hub, but through the science department? Yes?
Yes.
And it's called group tutoring?
Yes.
And it's once a week?
It's not weekly. It's only before the exams. So I've only done it twice.
Yeah, it's like the night before. He didn't even tell us, not you, my teacher didn't even tell us tutoring was going to happen until the day of.
Yeah.
It was so stupid. I was like, I can't make it. I'm working. So they need to be, you need to get him to tell us earlier.
Well, yeah, you see, I didn't know. I didn't know either.
I didn't know either.
Yes. I didn't know either.
Is there another group tutoring for chemistry that happens? It's just before tests and it's just you.
It's just me
And
before organic chemistry exams.
And it's organized through the science department, not through the Buck Hub. But you bill it through your stuff in the Buck Hub.
Yes.
Okay. I have a lot of questions. But I'm glad that you're doing it. I'm sure it's helpful when the students can make it. Okay. Y'all, the place that being inside my head is not a great place to be. It's like this all the time. Okay, so we're going to do strong induction now. The difference in regular induction and strong induction, we've kind of talked about this, is that for strong induction, you don't just step back one, you could step back more than one. So in regular induction, what we do is we assume that we can get on the ladder and that if we're on a step, we can get to the next step, right? So for strong induction, you assume you got to show that you can get on the ladder, and then you want to assume that you have gotten to all of the ladder rungs behind you, and that if that's true, you can get to the next one. So it's a stronger. What's the beginning part of a statement? Conditional. You get to assume more conditions. Which you don't want to do if you don't have to do, because that makes your proof seem sort of like hand wavy. So if you don't have to assume more things, you wouldn't want to. But sometimes you need to step back a couple of steps in order to get to the next ladder rung. Like maybe you're a hopper, and so you need to go back to hop to the third one. You get what I'm saying? Yeah. Let's not look at this Fibonacci sequence example because it isn't right, I don't think. I don't know. Maybe you guys can tell me how I've done it wrong, but I can't make this statement be true. I can't claim, I can't prove this. But maybe you can. Let's try. So you know the Fibonacci sequence? Do you? The Fibonacci sequence is like this is how like anybody tries to make math accessible to anyone. Fibonacci sequence is found in nature all over the place. The golden ratio stuff is here too. Fibonacci sequence is you add terms and you get the next term by adding the previous two. So like it starts with 0 and 1. I'm just going to do this here. It starts with 0 and 1, and you get the next term by adding the previous two, so it's 1. And you get the next term by adding the previous two, so that one's 2. And you get the next one by adding the previous 2, so that's 3, and then 5, and then 8, and then 13, and then 22. It's 22, right? 21. 21. And 40, 34. I am embarrassing myself. I'm going to stop trying to add in my brain. Okay. What? Is that wrong? Oh, okay. I was like, crap. Okay. So, if you plugged in, like this is 0, 1, 2, 3, 4. So f sub 4 is going to be f sub 4 minus 1. Ooh. Plus f sub 4 minus 2. So it's these two added together. This is called a recursively defined sequence. It's defined, the term you're on, it depends on the ones before it. So it's defined recursively. When sequences are defined recursively, you often need to use strong induction because to get to the step you're on, you need the previous two. So you need more than one. So you're going to assume all the ones up to a certain point. This says for n greater than or equal to 1 that f sub n is greater than or equal to 3/2 to the n minus 1. I don't believe that this is true, but let's make sure of that. F sub n, so we're going to prove this is true for n equals 1. F sub 1 is 1 that was given to us. Is this actually greater than or equal to 3/2 to the 0? Yes, right? That would be 1, which is fine. Yeah? But I can't make this be true for n equals 2. For n equals 2, f sub 2 is 1, right? Yes? But 3/2 to the 1 is 3/2. 1 is not bigger than 3/2. Right? Am I doing something wrong? Right. But that is 3/2, right?
Yes.
So I'm not really sure, and I tried to figure out what this like. Have I missed a subscript when I was typing something? But I did it over and over again. Like these all match. It doesn't work for n equals 3 either, because that would be 3/2 squared, which is 9/4, which is what, 2 1/4, and f sub 3 4. What did I say? Oh. Yeah, that would be 3, right? No, 4. Shoot, I gotta write something down. No, I told you my brain is a weird place to be. This is n equals 0, n equals 1, n equals 2, n equals 3. F sub 3 is 2, and 3/2 to the 3 minus 1 is 3/2 squared, which would be 9/4, which is going to be 2.25. Yeah. So we're all noticing that 2 is certainly not greater than 2.25. So, like, what have I just got that inequality symbol backwards? Does this keep working the other way? I'm like, who cares if it does, I guess. F sub 4 would be 3.
I feel like you maybe didn't do the F sequence in the middle. You probably just plugged in whatever n was, so 2 in the middle, because then it would work.
Like if I was,
If that was just 2 when n was 2, then it would work.
yeah, do you think that well, I didn't do this. I copied it from something else, but I copied something wrong. Yes.
So, here's my thought. If it requires the first two returns behind it, right?
Yeah.
I think that we have to have 0
Yes.
to be able to do the other stuff.
Yes.
So n of 0 would be that first one. What if we did that?
So n equals 1 is 0, and then n equals 2 is 1. So
We need n equals 1 is 0. No,
n equals 0.
saying like
Shift it over.
I'm with you. That this would be n equals 0.
Right.
But the sequence is already defined, and you have to have 0 because of the way it is defined recursively. But maybe this, and this would be true. It does specify for n bigger than or equal to 1, but maybe it should. I am thinking that this should be f sub n plus 1, which would do the same thing you're saying, but doesn't change the sequence, just defines which thing we're talking about. Or this should be n minus 2, maybe. But that doesn't work. So change this one to f sub n plus 1. I don't know. I'll think about this later. But this is not true, so we're not going to do number 3 because we can't prove it because it's not true. Well, we are going to do some strong induction examples because you're like, well, what are we going to do? Strong induction. We will. Don't worry. Yeah. So regular induction, you assume P of K is true. So assume it's true for some K, show it's true for K plus 1. Strong induction, you assume it's true for all I's up to some K. This K is your base case, says. And then you're going to show it's true for K plus 1. A lot of times in strong induction, especially if it's defined recursively, if you're going to have to step back, you have to prove enough base cases to establish a property before you so you're not going to have just one base case necessarily. So if n is an integer greater than 1, then n can be written as a product of primes. We're going to just jump in. I'll leave space for, will I? Should we do scratch work? Tonight I'm asking you. No. Yes. Okay. Me neither. Okay, if n is an integer greater than 1, then n can be written as a product of primes. So for our base case, what is n? N is 2. 2 is the prime. So we're done. Good job, everybody. Way to go. You don't, thankfully. All right, so 2 is prime. So we're done. Alrighty. For the inductive hypothesis, we are going to assume for all I with 2 less than or equal to I less than or equal to K that I can be written as a product of primes. Okay, so the base case is the same as it was before. For the inductive hypothesis, we are assuming it is true for a whole bunch of Ks. We're calling them I's, for a whole bunch of I's up to that K that we were using before. So a whole bunch of I's up to K, we are assuming that I can be written as product of primes. Do you have questions about that? Start at your base case, go up to some value K. Start at the end of your base cases. In this case, the voice n equals 2. Okay, and then what do we want to show? And when we do induction, what's the n that we actually show eventually? Yeah. So we want to show that k plus 1 can be written as a product of primes. This is kind of fun. K plus 1, if it's prime, we're done. If it's not prime, it has 2 factors that are smaller than it. Yeah. And those 2 factors that are smaller than it are i's. So it's a product of primes. Yeah. So k plus 1, if it's prime, we're done. If k plus 1 is not prime, then there are, so 1 less than a less than, or 1 less than a or b, which is less than k plus 1, that a times b is k plus 1. But this means that a and b are greater than or equal to 2 and less than or equal to k, because this inequalities are strict, and these are not, you know. Right, so these strict inequalities mean you can scooch to the next integer and it becomes inclusive. Yeah? And then this A and this B are both hit by the inductive hypothesis, so each of these can be written as a product of primes, and therefore k plus 1 is a product. Cool? Corey, what do you think?
Sounds good.
Sounds good. Proof. We will prove by strong induction that for every integer n greater than 1, n can be written as a product of primes. For the base case, let n equal 2. Since 2 is prime, we are done. We're trying to show it's a product of primes. It is prime, so it's a product of primes. Okay, so for the inductive hypothesis, assume for all integers I with 2 less than or equal to I less than or equal to K that I can be written as a product of primes. Consider K plus 1. Now, if K plus 1 is prime, we're done. If K plus 1 is not prime, it is composite. Therefore, there exist integers A and B with 1 less than A, B less than K plus 1, such that K plus 1 is A times B. Now, 2 is less than or equal to A and B, which are less than or equal to K, so both A and B can be written as a product of primes by the inductive hypothesis. Therefore, then K plus 1 is also a product of primes. We have shown, boy, my hand hurts, shown by induction, strong induction, that all integers n greater than or equal to 2 can be written as a product of primes. We're doing so well. We're going to be good to go. We got time for another one before we go, right? Do you have any questions about this strong induction proof? I think the strong induction proofs are on homework 11. Anybody confirm that? I believe that's right. I think I just put regular induction on homework 10.
Yeah, that's strong induction.
Yeah.
I think all of them are strong.
Yeah, 11 is just 5 questions. I think they're all strong. They're both 10 and 11 are only 5 questions. 10 should be 5 regular induction, and 11 should be 5 strong induction. You could do them all before Monday and then ask me about them Monday. I think you'd be ready for that. Because I normally leave off 5.6, 5.7 anyway.
How can they know which one to choose?
Which one, what to choose? Strong induction or regular induction? Well, I'll tell you for now. For now, as you're like getting used to it, I'll tell you. But like, when you see stuff like this, where everything is defined recursively, you're gonna need it, because to get something true about this, you need to know it's true about the two things in front of it, and so you would need strong induction in order to do that. Other times you don't, like this one too. So it's obvious, it's more obvious when you are looking at recursively defined sequences and stuff, and you're trying to prove something about them. But like on this next one, I don't know that it is totally clear until you start. So let's talk through that one. So we've got every integer greater than or equal to 12 can be written as 4a plus 5b for some non-negative integers a and b. So the reason that regular induction does not work here, you would assume it works for 12. Great. Show it 4 times 3, 5 times 0. We're good to go. Yeah? Your regular induction would say, okay, well, after that, maybe that's not the one we should use. It's because we can't use negative integers. If you wanted to say this was true for any a and b, like I think you can make it work. But for non-negative integers a and b, you can't, because you can't make b go negative. Let's talk about this. Do you want to go from 12 to 13 or whatever? So you're going from some number to another number, right? You want to say, well, on this step, take away a 4 and put a 5 in on the next step. That makes sense, right? Because that would move you by 1. Yeah? So take away a 4, put in a 5. Well, what if you were on 15? You don't have a 4 to take away, right? So you can't step back just 1. You need to step back a multiple of 4. And to do that, you need to know that you have that much space to step back. Does that answer it a little bit? So you don't always know, but you're learning how to do this, so I'm going to tell you, use strong induction or use regular induction. I don't like when people call it weak induction, because that seems unusually cruel. Like, we don't need to do that. So anyway, let's do this one if we have time. Okay, so I'm going to leave space, Janiyah, but I'm probably not going to write any scratch work. So we are going to show by strong induction that for all integers x greater than or equal to 12, there exists, wow, oh no, it's going to get weird in pre-cal. It's fine. There exists a, b, and z, non-neg, z greater than 0, greater than or equal to 0. I can't get an eraser. There we go. Now I can't make it go away. Such that x equals 4a plus 5b. This question I took out of context, but it was like you can use 4 or 5 cent stamps to mail it for any postage greater than 12 cents. That's kind of stupid, but whatever. That's why I took it out. Okay, adding context that's irrelevant to whatever. Anyway, Are there even 4 and 5 cent stamps? Like, I don't know. Like, why are we doing this? Oh no. Oh, oof. We gotta hurry. No more stalling. Okay, my iPad's gonna die. What we're gonna do for this is we are gonna show this for 12, 13, 14, and 15, and I'll show you sort of why. For the base cases, let n equal 12, 13, 14, and 15. Notice 12 is equal to 4 times 3 plus 5 times 0. 13 is 4 times 2 plus 5 times 1. 14 is 4 times 1 plus 5 times 2. And 15 is equal to 4 times 0 plus 5 times 3. It's like this give and take things why we're doing minimum number of 5 cent stamps, minimum number of 4 cent stamps. And then, okay, so that's the base cases hold. Now, assume for all I with 15 less than or equal to I less than or equal to K. I'm starting at the end of my base cases because I've already proven it for these other ones. That I equals 4A plus 5B for some A, B, and Z non-neg. Using 2 different notations for that in one problem's nice. That's just for you guys. I gotta find my brain before pre-cal. It's gonna be a long day. It's fine. It'll be fine. Okay. So we are gonna look at K plus 1. We'll step back 4, 3. K plus. I want to add a thing there. Ooh. My iPad's for sure gonna die. It's not dead yet. 9%. Ooh. Okay. Okay. I am gonna step back 3. This is, I can write this as K minus 3. Oh, I've lost the thread on what I'm doing. This is fine, right? We've got K plus 1, which is going to be, I subtracted 3 there, but I also added 3, so I haven't changed anything about what's going on. We good? Okay, but this is one of my I's. Yeah. And even if I'm on 15, I can step back 3 and still be in the things in my base cases that I've proven. So I know that this is equal to 4A plus 5B plus 4. This part is the 4A plus 5B from the inductive hypothesis, and then this is 4. That's the reason that I went back 3, is so that this thing I'm adding on would become a multiple. I could also go back 4 so that the thing I'm adding on could become a multiple of 5. Right, like I would be adding on 5. Because I'm going to group this in there with that A. So this is equal to 4 times A plus 1 plus 5b. And now A plus 1 and B are in xenon neg. Oh boy. So we're done. We have shown for all n greater than or equal to 12 that n equals 4a plus 5b for some a and b in xenon neg. Yes. Find a box. And right on time. 12:20. Okay, do some homework. Email me if you need help. I'll see you guys on Monday.
Everybody have also 4 and 5 cents.
Right. You'll know.
I run into that problem all the time, man.
I know.
I just bought a book again for $15.
For what? Yeah. Inflation and stamps has been crazy too. What? What are you trying to figure out?
Like how many stamps are like in a book?
It's 20.
20.
You need $15 for 20 cents.
That's not right.
It was like 14 cents with the tax, you know.
Yeah,
You get stamps.
that's cheap, I think.
That's cheap. What? $15 for some stamps.
I think a book is 20 stamps, and they should be. They're 45 cents each.
Oh, so I forgot I did some of the homework, like back 3 on it. You want to run up and staple my 2 sheets?
Oh no, I'll just put them with this.
Thank you so much.
Of course. Bye. Y'all have fun in calculus. Oh my gosh, I'm still in Teams.